All right, good morning, everyone. Can you hear me?
Yes.
Good morning.
You can hear me? Sorry.
Yes.
All
Yeah,
right,
we
thank
can
you.
hear you.
Sorry, just my volume was very low. Okay, so let's go ahead and get started. Just a reminder that the class has until tomorrow for anyone who's interested in the asynchronous mode to let me know that you will be interested in taking that mode under the specific terms that I explained in our last lecture. All right, and then whoever does decide to agree to those terms, I will then meet with those students virtually to discuss meeting times as far as to be able to answer questions. All right, so I'm going to go ahead and project our first lecture. All right, I can see it. Can you guys see the lecture?
Yes.
Yes.
All right. Okay, so to begin our story, we're going to focus on the atom itself, a rather simple representation of what's going to constitute the molecules that we will be focusing on as the course progresses. So let's talk a bit about the components of the atom, and there's going to be very much review for all of you guys. You will find this material in Chapter 1 of the Inorganic Chemistry textbook by Housecraft. All right, so what essentially is the atom? It is the smallest identifiable unit of an element. Okay, it's capable of existing alone, or, this is very important to recognize, in chemical combination with other atoms. And that is because certain atoms do not have the capacity to exist stably alone. We have about 91 different naturally occurring elements and greater than 20 synthetic elements. So here we have this really simplistic representation. So just imagine this depiction here as a sphere. All right, so that's our spherical representation of an atom, and where a large portion of that volume is where you can find electrons. So this is where the electrons would reside, as you can see here. And so that constitutes for this negative charge. Now, the way the atom is composed is a balance of charge. So you have a net neutrality. And so what's really balancing that charge is the presence of positive charge that exists within the nucleus. All right. So here you find the particles of the protons and the neutrons. Now, to note that neutrons, okay, are not located in all atoms. So for instance, protium, which is an isotope of hydrogen, does not contain neutrons. All right, so let me just go back here for a second. Just to note that there are smaller subatomic particles, but our focus will be on the composition of the atom with regards to the electrons. All right. Sorry, sometimes I have difficulty with this. Go back in and then back, okay. Discard. All right, so continue on our discussion about the atom. So as you all know, how we represent the atom with respect to the periodic table. And when we do meet in person, and for those that are not able to necessarily meet in person during regular scheduled time, I will be providing everyone with a set of handouts that corresponds to different lectures. So for this specific set of handouts, for this specific set of lectures, we do not have handouts. But one of the things that I want you to carry at all times is a periodic table, so that you'll be able to refer to it when we discuss certain periodic trends and properties of atoms. Well, the atomic mass is largely concentrated in the nucleus, right? And even though it constitutes a rather small portion of the volume of the atom. So just to give us a context, the atomic radius is about 10 to the 5 times the radius of the nucleus, right? So you can see how small the nucleus is with respect to the atom, and using the radius as the context. That being said, the nucleus of the atom contains a lot of density, all right? And so we want to quantify that. That is greater than 10 to the 12th times the density of lead. So lead is an element that is well known to be extremely dense. All right, so does anyone know where lead is applied in a medical context? Feel free to get into your microphone or to chat in the text. Where is lead applied medically?
I mean, I don't know if applied, but all I can think about is lead poisoning.
All right, so that is a context of where it can show its toxicity. But what about its benefits? Where do you see lead being used when you're getting, let's say, an examination, a medical examination? Thank you, Dr. Elise, by the way. Anyone else? Well, let me remind you, whenever you get an x-ray done, you have to have a barrier, something to protect you, right? Because the radiation can be quite damaging. So lead is what's used due to its density, as it can absorb the x-ray and can protect you from the harm caused by radiation. All right. So when we're representing the atom, or if you want to look at it from this other terminology, the nuclide, we use the specific representation here, where E is the symbol for the element, and then we have the letters Z and A. All right, so let's remind ourselves what that particular symbols mean. Sorry. All right, so Z stands for the atomic number, and A stands for the mass number. So Z equals to the number of protons, which also equals to the number of electrons. To remind ourselves that there is a charge neutrality, right? So every atom will be 0 in charge. A is the sum of the number of protons and the number of neutrons. Nuclides of the same element, okay, so same element means that you have the same number of protons and electrons, but different number of neutrons are called isotopes. And these isotopes have different natural abundances. Elements with only one nuclei are called monotopes. All right, so what you typically see represented as the atomic mass on the periodic table is an average mass based on the natural abundances of the common isotopes of an element. All right, so as I mentioned to you, what we're going to focus on primarily is the composition of the atom with respect to electrons. All right, so those particles are extremely important. So getting a sense of electronic structure will really help us to determine the properties of atoms. And if we think about it in a bigger context, right, more broadly, we start to appreciate the properties of atoms in their charged forms, such as ions, and also in terms of molecules, both neutral and charged. And so we can get a sense of the forces that exist between these species and within them. So an understanding of electronic structure, or as we will refer to also as the electronic situation, historically took place in two main stages. And the reason for this is because one of the biggest findings about the electron is the existence of the wave-particle duality. And so historically, this evolved through the perspective of the classic quantum theory and wave mechanics. All right, so let's review what exactly is classical quantum theory. So in 1901, Planck suggested that energy could be absorbed or emitted only in quanta of magnitude delta E, right? So these are going to be specific values of energy. All right, so if you recall from your previous courses, energy equals to Planck's constant times frequency. Frequency equals to the speed of light, or the velocity of light, divided by wavelength. All right, so a unit of energy, joules, just to remind you all of the values of Planck's constant, the units, the value of the speed of light or velocity of light. All right. One of the most important experiments that really helped to define the property of the electron in terms of its particle nature was atomic spectroscopy. All right, so what exactly was the spectroscopy? Essentially, this provided a perspective of each element being able to emit light of specific energies when excited by electromagnetic radiation. Rutherford and Bohr developed a model of the atom to help explain the atomic spectrum of hydrogen. All right, that's the simplest atom to be able to explore. But more broadly, this model of the atom was to help to explain the origin of the energies. So here I provide this really simplistic model of the atom, which at the time was quite useful to give an understanding of this idea of the composition of the atom with respect to where the electrons are located and how they exist with respect to the positively charged nucleus. All right, so here what we're looking at in this model are these spheres, excuse me, these orbits. Okay, so here, 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 that exist at fixed distances from the nucleus. And so each of these orbits are labeled n equals to 1, n equals to 2, n equals to 3, n equals to 4. So these integers, all right, at a fixed distance away. All right, so let's explore the details of this model. So according to the model, electrons travel around the positively charged nucleus in stationary circular orbits. All right, so these orbits are fixed and they exist at a specific distance from the nucleus. Well, what was observed was that the energy of each of these orbits is essentially quantized. So as you increased in the value of n, okay, so which orbit you exist in, right? And the further away you are from the nucleus, the greater the energy, okay? So the electron may absorb light of specific energies and be excited to orbits of higher energy. All right, so let's explore this. All right, so here I'm just giving you a perspective of the difference in energy from the orbit n equals to 1 and the orbit n equals to 2. And as you can see, there is a fixed energy difference that I have here as represented by delta E. Well, what can happen is, let's imagine that electron in n equals to 1 absorbs electromagnetic radiation, okay? So it absorbs energy, and so it gets promoted into a higher energy orbit. So here we have what is a representation of the absorbance. N equals to 1 moving to the n equals 2 orbit, n equals to 1 moving to the n equals to 3 orbit, n equals to 1 moving to the n equals to 4 orbit, all right? So that represents an absorbance of the energy in order to move that from a lower energy orbit to a higher energy orbit. Well, then you have what is known as an emission, all right? So what is an emission? Essentially what that is a relaxation of the energy of the electron from a higher energy orbit to a lower energy orbit. So that energy that the electron has acquired to go into the higher energy orbit is released. And how is it released? Well, as depicted here pictorially, it's just a cartoon, the energy is released in the form of a photon, something that we can visualize, all right? And so that is what constitutes the emission spectra, all right? So as the electron emit light of certain specific energies, as they fall to orbits of lower energy, we obtain what is known as the emission spectrum. And so here is the representation of those lights that are observed as a consequence of this atomic spectroscopy. Rydberg decided to develop a simple equation to help predict the wavelengths of the hydrogen emission spectrum. So according to that equation, 1 divided by the wavelength that corresponds to the emission equals to RH, which is a constant, times 1 divided by n sub 1 squared minus 1 divided by n subscript 2 squared. All right, so let's define the details of this equation. So the first part of this helps us to get a measure of the energy, right? So from the perspective of wavelength, right? There's a correlation between energy and wavelength, as I already showed you previously. But those um, N1, N2 values, those are the integers. And what specifically are they? Well, they are the quantum numbers, right? They define the orbit in which the electron exists in. And the way this particular equation was written, N sub 1 is lower in value than N sub 2, okay? So we're looking at this from the N sub 1 representing the lower energy orbits and the N sub 2 representing the higher energy orbits. And then here's the value of Rydberg's constant for hydrogen. All right, so this particular equation was developed in order to be able to predict the wavelengths, or more broadly, the energies of the corresponding hydrogen emission spectrum, those lights that I showed you in the previous slide. All right, but then another experiment was done that really perplexed many people. And by perplexed, what I mean is it confused people, because the Bohr model of the atom suggests that the electron is a particle and that it goes through fixed orbitals in terms of its presence with respect to the nucleus. But then an experiment was done, which is known as as an electron diffraction experiment, right? But that was not necessarily what they expected to observe. So in this experiment, what was done was that electrons were passed through a slit, okay? And the expectation, right, or the hypothesis was that what you would see as it goes through the slit and gets detected by a detector of sorts was that you would see these fixed particles hitting the detector. However, what was actually observed was this diffraction pattern, okay? A diffraction pattern that is indicative of something that is wave-like, okay? And so what this suggested was that the electron, in addition to featuring properties of a particle, also had properties of a wave, right? This whole particle-wave duality. And so this particular experiment was very important in terms of showing that wave property of the electron. So how do we account for this, in addition to account for the particle nature that we previously observed in terms of the Bohr model? All right, so previously, Planck and Einstein showed that light exhibited a wave-particle duality. In 1924, Louis de Broglie argued the same for the electron. And so what he did was to develop an equation to represent this type of duality. So here in this equation, we have the wavelength equals to h Planck's constant divided by mv. All right, so let's define this a little bit more closely. All right, so we have the unit of meters, all right, for the wavelength. We have Planck's constant. But in addition to these terms that we associate with energy, we also have these two additional factors to consider. M, which corresponds to the mass of the particle, and V, which corresponds to the velocity of the particle. So here we have the combination of these two features, the particle nature, but also the wave property. In addition, as you all are familiar with, is Heisenberg's uncertainty principle. So according to this principle, if an electron has wave-like properties, it is impossible to know exactly both the momentum and position of the electron at the same instance in time. All right, so taking this into consideration, this is quite distinct from the concept of uncertainty, right? Uncertainty is that the
Professor, you're muted.
All right. Can you hear me now?
Yes.
All right. Sorry about that. Just shut down for a quick moment. All right. So what we were talking about was this idea of how now considering this wave mechanics, Heisenberg's uncertainty principle, how we're moving away from the concept of these fixed orbits with fixed energies in terms of the location of the electrons. So now we have to consider this idea of the probability, okay, the probability of finding the electron in a given volume of space. So here, we're now moving away and defining this concept of what is known as orbitals. All right, orbitals, as opposed to precise orbits of electrons. So what exactly are orbitals? Well, these are regions that describe the probable location of an electron. All right, so let's be clear about that, the probable location of an electron. So that idea of probable, the probability, fits in with Heisenberg's uncertainty principle, where you don't know exactly both the momentum and position of the electron at an instance of time. And so when we start to consider this concept, what we can do here is calculate the probability of locating an electron within the atom. All right, so let's explore this in terms of wave mechanics. All right, so a really important equation that you all will explore more closely in physical chemistry is the Schrödinger equation. All right, so this particular equation helps to describe the wave properties of an electron in terms of its position, mass, and total energy. And when we're talking about total energy, we mean both the potential and kinetic energy. All right, so as far as the kinetic energy, essentially what that means, the motion of the electrons within the atom. And then as far as the potential energy, we're referring to the that attraction between the electron or the electrons with respect to the positively charged nucleus. All right, so let's look closely at this particular equation because it's a rather simple one, but there's one that often people get a little bit skeptical about just because it can become a little bit complex. But let's look at this with respect to the simplicity of what we're specifically talking about. Because we're focusing on, let's focus on our little model, the electron with respect to the positively charged nucleus. All right, so that volume or that probability of the electrons interacting with a positively charged nucleus in terms of an electrostatic attraction. All right, so in this equation, focusing on the wave function, the wave function describes an electron wave in space. Okay, so essentially the wave function is a representation of the atomic orbital. The term H in this equation refers to a Hamiltonian operator. All right, that sounds complicated, but it really isn't. It's simply a mathematical function. And so this mathematical function includes derivatives, right? So that term you guys all heard in calculus, that operate on the wave function. So this is something that is applied to the wave function. The output of this mathematical formula is that you are able to determine the energy of the electron. Okay, and so essentially your product, your result from this mathematical function is that you get a value of energy times the original wave function. Okay, so again, that energy has to do with the total energy for the electron. Now let's look at this more closely. Different atomic orbitals will have different wave functions. That makes sense, right? As we're all familiar with atomic orbitals, it's something we're well aware of, s orbitals, p orbitals. They all have their different corresponding energies. And so as we can expect, when you apply a Hamiltonian to different wave functions, we expect to have different values of energy. Again, keeping in mind the model, the electron in terms of its interaction with the nucleus within the atom. All right, so in order to explore this more closely, okay, what we're going to look at, excuse me, didn't mean to go back. What we're going to look at is the Hamiltonian, so that function for one electron system. All right, so again, here we're looking at this simple model of one electron with respect to the nucleus. Okay, so here is the formula for that Hamiltonian. And so we break it down into its composition. We have terms that refer to the mass, the distance from the nucleus. So I have a little typo here, from the nucleus, and then the electron charge, right? So we're essentially focusing on that probability of the location of the electron with respect to the nucleus. All right. So what we're going to see is how we can break down this Hamiltonian to the two components of energy. So this part that I have circled here in blue describes the kinetic energy of the electron. Again, that has to do with the energy of its motion. Whereas the other part of that equation that's circled here in red, that has to do with the potential energy that due to the electrostatic attraction between the electron and the nucleus. All right, so that's just to give us a perspective of what part of this formula has to do with the calculation of the kinetic energy, what part of this formula has to do with the calculation of the potential energy. And again, the same terms that we looked at already. Now, it's best to evaluate this particular formula by considering spherical polar coordinates. All right, why am I saying spherical polar coordinates? Well, because basically we are trying to predict a probability of where we can find an electron. So we're looking at this from the perspective of a positioning. When we apply spherical polar coordinates here, we can define a certain position in terms of its distance from the origin. So the origin in this context, think about that being the nucleus, right? So again, this type of model. But we also can define that positioning with respect to two important angles. One of these angles here, B, has to do with the angle of that particular positioning with respect to the plane, the XY plane. And then the other angle, pi, has to do with the perspective of the positioning of that particle, that electron, from the perspective of the z-axis. All right, so this is useful in order to give us a sense of location of the electron. Okay, so now we can rewrite this wave function for a monoelectronic atom. Remember, that's our focus, which is a very simple situation, a simple electronic situation, one electron in an atom. And so an atom that falls under that category is the hydrogen atom. So here we're going to focus on the interaction between an electron and the nucleus. So now we're going to have our wave function broken down into two parts in polar coordinates. The two parts are the radial and the angular components. All right, so the radial. So we have this now rewritten in terms of the radial wave function with respect to r, that distance from the nucleus. And then we have the wave function with respect to those two angles from the spherical coordinate, polar coordinates. So more simply, we have the radial wave function and then multiply by the angular wave function. All right, so we're going to keep this in mind because we're now going to look at the radial, and then we're also going to look at the angular component of the wave function. For us to dive into this more deeply, we have to remind ourselves about quantum numbers. So three important quantum numbers help us to discuss the wave function. So n is the principal quantum number. You're all are well aware of this. We also have L, and L is a measure of the orbital angular momentum, but also it's a representation of orbital type. All right, so to remind ourselves, here I provide a little table where we look at the value of L and what type of orbital is represented. So L0 represents the s orbital, L equals to 1 represents the p orbital, L equals to 2 represents the d orbital, right? So we're just focusing on this. These are things that you are all aware of. Now, in terms of the value of L, so L is connected to the value of n. So L can range in numbers, and it can range from a value of 0 all the way up to a value of n minus 1. All right, so just think back to your general chemistry. You have all seen this previously. There is an additional quantum number. So here we have the m sub L. That is the magnetic quantum number, and it determines the orientation of the orbital in space. All right, so that's going to be very important. I mentioned to you in our first discussion this idea of symmetry, and we're going to look at it in a moment. So the location, the directionality of orbitals is going to be very important. So here in this course, you're going to be very careful about how you draw your orbitals, because that would dictate some really important properties about atoms, and also how those atoms can interact with other atoms to form molecules. All right, so we're going to keep that in mind, and we'll look at it more closely in a moment. All right, so the values of m sub L can range from negative L up to positive L. And so you can have a total of 2L plus 1 number of these values. Right, so that, just keep this in mind. All right, so we're going to focus on the hydrogen atom as our representation of an atom with one electron. So again, a monoelectronic atom. And we're going to focus on the radial part of the wave function, right? The distance in terms of radius between the electron and the nucleus. Remember, where can we think about the probability of finding these electrons? Well, we're not focusing on the Bohr model being fixed orbits. We're thinking about orbitals, right? The probability. And so if you remember, they can be the 1s orbital, the 2s orbital, 2p, so forth, okay? But if we're focusing on the hydrogen atom, then we're focusing on the 1s orbital as the most likely to be the one where you will find your electron. So that's where we're going to focus our probability. Okay, so focusing then on a 1s orbital, okay, we know that the 1s orbital is spherical. And so let's define the quantum numbers. So n equals to 1, L equals to 0 is the only possibility, and m sub L equals to 0. All right, so these are the three quantum numbers that we can keep in mind. And so we also then have to look up the radial wave function for the 1s orbital. And so this is what I've provided for you guys here. So when you look at your textbooks, okay, you will see this equation. And so I will, again, we'll provide you all with the textbook right after class. So if you don't have a copy of it, I'll provide you with a PDF. So you look up the wave function for the orbitals, and there's one that you will find for the 1s orbital. Okay, there's a radial wave function. All right, let's define a few features of this particular equation. Here we have K1s, which is a constant that pertains to the 1s orbital, times e raised to negative z times r divided by a naught, where z is the nuclear charge, a naught is the radius of the first Bohr orbit. Okay, so the first Bohr orbit of the hydrogen atom. Let me put that here. Okay, all right, so now we have that in mind. But let's focus on the features of the equation. What I just described were the parts of the equation, but not the features of this equation. All right, so let's again draw a little simplistic model so we don't lose our perspective. Okay, so we're focused on the radius, right? So that's why the radial wave function. But one of the features that you can see of this equation is that there is an exponential like decay. So if you look at this part of the equation, it reveals that there exists an exponential decay. Another really important feature is that as you increase in the value of n, the primary quantum number, what you will see is that there is an increase in the most probable radius of finding the electron. And that makes sense, right? If you think about an electron existing in a higher energy orbital, right? Higher energy orbitals are located in terms of the their probability further away from the nucleus. Another feature that's not obvious, if you look at this equation, are what are known as the radio nodes. A radio node, or in general, the nodes, okay, nodes refer to a zero probability of locating an electron. Okay, and so what I'm going to provide here is just some specific numbers that you can keep in mind, but a general expression here that defines the number of radio nodes in terms of the values of quantum number n and quantum number L. So number of radio nodes equals to n minus L minus 1. Okay, it's very important to keep that in mind. So you can simplify this. For instance, if you have an electron and within the ns orbital, well then, if you're applying this equation, that would be n minus 1 radio nodes. If you're in the np orbital, well, that would be n minus 2 radio nodes. And how do I know that real quickly? Because I know the value of L based on the orbital type. Nd, well, n minus 3 radio nodes. Nf, n minus 4 radio nodes. All right, so now let's look at this more closely. Well, for all orbitals other than the s orbital, okay, so for all orbitals other than the s orbital, the r wave function, or the radio wave function, is equal to 0 at the nucleus. In other words, there is a node right at the nucleus. Okay, and that's not actually considered a radio node. I'm going to take note of that. Not considered a radio node. All right, and this is true of all orbitals except the s orbital. All right, so now let's visually see this, because these are all words you're probably having difficulty understanding. What am I referring to? All right, so let's look at specific examples. All right, so we're going to evaluate radio nodes. We're going to do this together. All right, here is the graphical representation of the radio wave function for the 1s orbital. All right, everyone, I want some volunteers. What is the value of n for the 1s? What's the value of n for the 1s? Excuse me?
1.
Okay, good. Who was
1.
that? Okay, so a number of people. I see
Hold on.
Angelica posted in the chat. Okay, let's see. What about the value of L?
Zero.
0. Good. All right. So we have this. N equals to 1. L equals to 0. All right. So then, how many radio nodes can we predict, or can we calculate?
0.
Okay. So what did you do? Well, you apply this equation that I just showed you. N minus 1. Excuse me. N minus L minus 1. And when you apply those numbers there, you get a total of no radio nodes. Probably I should put radio in here. All right. Well, how do we see that graphically? What are we seeing here? Well, what do we see is that because we have the s orbital right at the nucleus, right? Well, we have a positive value. Is a non-zero value, okay? And then as we go at r distance away from the nucleus, so we're moving in this direction, and we're moving away from the nucleus, you see that the probability, because remember, this is a measure of the probability of finding that electron. Well, the probability decreases, but it never actually touches 0. It comes close to touching 0, but it actually never equals to 0. All right, so that's what it means that there is no radio nodes. So we see the exponential decay. And we also see that there is a non-zero value here. Okay, and this is being the s orbital. All right, you guys did very well there. Let's move on to the next example. The 2s. All right. So what's the value of n for the 2s?
Two.
Very nice. So value of 2. All right. So we have that. N equals 2. L equals 0. Then we calculate the number of radio nodes, n minus L minus 1, and that's going to give us a total of 1 radio node. All right, so let's look at that in terms of the graph that we have here. So we have the wave function. Again, we have a non-zero value at the r equals 0. We have the exponential decay, okay? But we also see that we actually do cross the value of 0. And so that is our 1 node. All right, keep that in mind. All right, you guys are doing very well. Okay, so what about for the 2p orbital? Okay, so you guys already know that for 2p, n equals to 2. Okay, what about the L? What's the value of L if you're in the p orbital?
1.
Very nice. Okay, and so we use our formula to determine how many total number of radio nodes, and so we have a total of 0. Let's see this in the graph itself. So these are the type of things that I want you guys to think about, is interpreting the graphs. It's not just want you to calculate this. Well, show me in the graph how this is the case. Well, then we see that in terms of the actual graph, the distance away from the origin, we never have a value of 0, okay? But at the origin, we do have a value of 0. Can somebody explain that? Why is that the case? Why do we have a 0 value at the origin? Who's the brave soul to give me an answer? Why is this? Okay, how about, what is the shape of a p orbital? What does it look like?
Like a dumbbell?
Like a dumbbell, okay, good. So let's go a little bit more in depth. Let me just give you a drawing. Okay, and we'll look at this more closely. I'm shading in one of these lobes. So we have these 2 lobes, and in the middle, we have a dot. That middle represents the nucleus. But if you notice that there is a section right here where there is no electron density. Well, that is reflected here. That at the origin of a p orbital, there should be no probability of finding electrons because there is no location for it to exist. So remember what I said. Every orbital except the s orbital will have a node at the origin. All right, so that's what we're seeing here. This is not a radio node, but it is a node in general. All right, the 3s, okay? So the 3s, we're gonna go through this now more quickly. We have a
I'm sorry. You said that when there's no space for electrons, it's gonna be like a space. It's not gonna meet 0, or the other way around.
I actually don't understand your question. Can you repeat it? Oh, one other thing to just everyone in the course, you can definitely speak to me in Spanish if you need to clarify something. I speak both languages, so go ahead.
I don't even know how to say it in Spanish. It's what you say about the electrons. You say, oh, the electrons are missing here. Like there's no space for electrons. So where is that represented?
Right, but I don't quite understand your question. Are you asking me what a node means? Because a node represents a location where no electrons can exist, no probability for
exactly.
Electrons. Okay, so a node, that's what it means. A radio node represents where at a distance away from the nucleus, there is no probability for electrons. And then I explained to everyone that for the exception of the s orbital, all other orbitals have a node right at the origin. But that node that exists is not called a radio node.
Okay, thank you.
Okay, all right, but I wasn't actually referring to you. I just wanted to make it clear, anyone, feel free to speak to me in either language, whatever is most comfortable for you for clarity, okay? All right, so going to the 3s orbital, we here have determined that there are 2 nodes, and then we're going to look at all the features, okay? So as you can see here, you have 2 nodes. These are your radio nodes, right? Because this is an s orbital, you see that the value at the origin here is non-zero, okay? And then you also have the features of an exponential decay, right? So everything that we've talked about is encompassed in this particular graph. All right, so I want you guys to be able to interpret graphs, what they mean. It's not just going to be a straightforward calculation. All right, you guys did very well.
I have a question.
Yeah, go ahead, Juliana.
When you say a radio node, because at first like in the first graph, the one in the slide before, I thought that the radio node was like every time like there was like como una bajada under the x.
Es cuando cruce cero. Tiene que tocar cero.
Exactly, but it's like
En una
the
distancia del núcleo, no el origin. Un radio node
Exactly. It doesn't
significa una
mean
distancia del nucleus.
because I thought like if it had 2 nodes, it would be like 2 waves, like, but it's like 2 points that go below 0, right?
No, that's incorrect. The actual radio node has to be one where the value is 0.
Exactly, but it's
It's
not
not
like,
just that it's going below that value. It's that it actually touches 0. Okay, that's the key thing to remember.
It's not like there are gonna be 2 waves that like go down.
Yeah, and at no point were we talking about more than one wave. Remember, we're referring to one wave as a representation of an orbital. Okay, so there's a wave function that corresponds to a specific orbital. So there wouldn't be more than one wave. It would just be one wave that we're talking about representing that particular atomic orbital. Okay?
Okay. Yeah.
All right.
Thank you.
No problem. All right, so another way that we can look at this is by basically squaring these wave functions. So what is known as the square wave function. All right, so you can look at it as the whole wave function squared, or just even focus on the radial wave function part of it being squared. So when we do that, that's called the probability density. And so just as another representation of the likelihood of finding an electron. So mentally, when you square all of these values, right, all the values will be positive, right? So that was something that Juliana was asking me about. What does this mean? So it means that just that where there's an actual part that is a 0. So let's say that we wanted to square this. When you square this, all of this graph would be actually positive in terms of its value. Okay, so just keep that in mind. All right, but focusing on specifically the radial probability function, right? Another way that we can represent this, again, we're thinking about one electron with respect to the nucleus. Well, the radial probability function. So we can look at this from the context of imagining the atom consisting of onion layers, right? So as opposed to Bohr's model, right? Bohr's model were these specific orbits, right, where you found the electrons at a specific distance. Well, go away from that, but how about think about this 3-dimensional structure where you have these atomic orbitals that we are depicting as these onion layers. And so we're looking at the location of the electron in these layers. So here's just a visual where we're focusing on one layer, okay? So that's why I have here as a layer. And what we're looking at here are these sort of concentric spheres. So remember, if you cut into an onion, you have all these little spheres around the center. So we're focusing on them as these concentric spheres with a given volume. And so we have a distance from the origin to the maximum distance of that particular layer. And then in addition, the layer here constitutes a specific amount of volume of the total volume of the of this particular model. And then you have a distance of dr, which represents the thickness, the radial thickness of that layer. All right, so this is another representation of thinking about orbitals, right, and the probability of finding of electrons within them. All right, so using this as our model, okay, this is our little model over here, and where our electron is with respect to the nucleus. All right, well, here we have the radial probability function, which is represented by this equation right here, right? So there's r squared, the radial probability. All right, so radial probability can be thought as the probability of finding the particle within an interval of length dr at a distance r equals to r naught. Okay, so we're trying to specify a specific distance here. All right, so again, the probability of finding that particle. Keep in mind that this particular wave function is squared. And so we're going to see what happens in terms of the graphical representation. Now, from this particular model is a little bit different than the other model we were looking at. As the value of r approaches 0, the value of the probability of finding the electron approaches 0. Okay, and why is that? And that's because the less space you have from the nucleus, the less likelihood you're going to be able to find electrons, right? There's going to be a point where there's not enough space for the electron to fit, right? That's just this sort of a way of thinking about it. They have to have a certain amount of space for the electron to exist. It has a certain dimension. From the other perspective, as you increase the value of r, and let's say you increase it to infinity, right? Well, when that happens, the probability of finding electrons will also reach 0. And why is that? Why is it going to reach 0? Because you're going to put the electron so far away from the nucleus, you're going to disrupt that electrostatic attraction between the electron and the positively charged nucleus. That is so far away that there is no attraction, and what's going to happen to that electron is going to be released. Basically, your atoms are going to become ionized, right? So what we'll see is an exponential decay in this graphic. And then finally, the maximum value of r is a naught. That's the atomic Bohr radius. All right, so looking at this graphically, and here I'm just showing you, we already talked about the features that we saw of the similar model that we were just focusing on. But just to review a few different things. So we have the 1s orbital, the 2s orbital, the 2p orbital. These are all being represented by this radial probability, right? So this is a function that is squared. So one of the details that we can see is that all the values that we have are positive. They never go below 0, right? That makes sense. We squared all the values, so we always have a positive value. All right, so then what other features do we see? Well, let's focus on the 1s orbital. We see that as you approach the origin here, your value is going to be equal to 0, right? Because you don't have enough space for the electron to fit. Then you have a maximum value of the probability, okay, and that's going to be at the value of a naught. That's the Bohr radius. Okay, so another feature you have is the exponential decay. And as I mentioned to you, as you go even further out, well, there can be no probability, right? Because then you essentially have no attraction between the electron and the actual nucleus. So you'll be even outside of the orbital. So this is just the details of the probability within the actual orbital that we have depicted graphically here. So you see very similar features in the 2s and the 2p. Okay, if you look at the 2s does have a location where there is a node, a radio node. Okay, so I just wanted to highlight this in terms of the radial probability. All right, so now that was focusing on the radial component of the wave function. Now let's focus on the angular component, the angular wave function. So here now, we are determining, or we're focusing on the shape of the electron cloud. So not simply the distance of the electron from the nucleus, but also the shape of that constitutes the probability of location. This particular wave function depends on the values of L and M sub L, but is independent of N. All right, so let's focus on this more closely. All right, let's focus on the s orbital. It's the simplest one to look at. So we know that the s orbital is spherical. And a term that we're going to apply, and we're going to use it a lot throughout the course, is this idea of a phase. Okay, and the s orbital, you've seen it in other courses, has a constant shading, a constant phase. just think about that as a constant distribution of charge. As it turns out, so remember thinking back to this spherical polar coordinates, right? Well, it turns out that the angular wave function for the s orbital does not depend on this angle, okay? It does not have an angular dependence. So the s orbital, as defined by the quantum numbers L and m sub L, L equals to 0, m sub L equals to 0, we look up in our textbook the equation for the wave function for the s orbital, and what we see here is that the value, the expression has no angular dependence. I'm going to just emphasize that, no angular dependence. Okay. Well, now let's look at the other orbitals. And as you can note, they will have an angular dependence. So here I'm showing you an example of a p orbital. And I'm being really specific here. I'm showing you the pz orbital. All right, so in this context, the p orbital, as we mentioned before, someone referred to them as dumbbells. Well, we'll be a little bit more precise. They are two tangent spheres, or they're not really spheres exactly. They're more oblong, but whatever. So there are these two spheres. We want to refer to it simplistically like that, with different phases. Right. So remember this term phase. What that means is that here we have, in terms of the coloration, they're colored differently. Right. So you guys have all seen this. Maybe you didn't really understand why, but think of it as them being opposite in phase, opposite in charge, right? And as we know for the p orbitals, there are three types of p orbitals. There are the px, py, pz. The one I'm showing you guys here is the pz. But why I'm emphasizing that there are three p orbitals? I'm emphasizing that because each of these orbitals in the atom will be equal in energy. And the term that we define, or that we use to represent equal in energy, is the term degenerate. Okay, so keep that in mind, because we will refer to that word degeneracy or degenerate throughout the course. All right, so since we are focusing on the pz orbital, all right, we're going to look at the quantum numbers. So here we have L equals to 1 and m sub L equals to 0. So we look up the angular wave function for this particular orbital, and this is the angular wave function. And as you can see, there is an angular dependence here. All right, so that's important to note. So it turns out that in angular part of the wave function, there are L nodal surfaces. What does that mean? L. Let me write this bigger so you guys can, for emphasis. L nodal surfaces. Well, we already defined a node, right? We defined the node as a location where there is no probability for electron density. Well, here in this context, this is an area with no electron density. So I talked about the p orbital before, so now we're going to look at it even more closely. We're referring to this pz orbital. At the origin, there is actually a distance between these two lobes, and that distance is defined by this plane. This plane is located on the xy plane, and in that plane, what we have is a nodal surface. Okay, or if you want to refer to it as a nodal plane. So this is a location where there are no electrons. Right? So from this context, and we're referring to at the origin, that node is an angular node. And so depending on the orbital type, the value of the nodes will be equal to the value of L. Okay, so I'm not showing you these orbitals, just want to emphasize the key points. The d orbital has 4 lobes, and it has a total number of a total value of L of 2, and so it has a total number of 2 angular nodes, or nodal planes, nodal surfaces. The f orbital, 6 lobes, has a value of L equals to 3 and has a corresponding number of angular nodes of 3. All right, so just to emphasize that relationship between the value of L and the value of nodal surfaces. And then very similar to what I described about the radial wave function, the same thing is true for the angular component. Whenever we square the wave function, that ends up being our best representation of orbitals. But I'm going through the details of the wave function, the radial and the angular components, so that we can see the contributions of the distance and also the contribution of the angles of these different orbitals. All right, so here is where we're going to touch and introduce this concept of symmetry. And so we're going to look at it from the context of the orbitals, and symmetry is a theme that will be discussed throughout the rest of the course. So first, I'd like to discuss it with respect to the orbitals. All right, when we're looking at defining the symmetry of an orbital, we're taking into consideration the phase of the wave function. And then graphically, we're taking into consideration the phase as depicted for that given orbital. All right, so orbital symmetry is defined with respect to an element known as the inversion through the center of the orbital. All right, what does that actually mean? So the element here is the center of the orbital. We all know what orbitals look like, but let's imagine that we are focusing on this square as our representation of an orbital, even though we know that no orbital looks like this. All right, so we have the square. What I want to emphasize here is we have the center. The center is the of this particular square. And what I want to focus on is defining what does an inversion mean. Well, an inversion mean is that you start off at some point, okay, from that center, and you're going to go through that center at an equal but opposite distance. So for instance, you go through the center, and then you're going to go an equal distance but opposite from where you started, okay? And then depending where you land, whether the phase is the same or different, is how you define the symmetry of that given orbital. All right, so here is this is what is known as an inversion. Okay, all right, so we did an inversion through the center. All right, so we're going to use these two terms to define symmetry. There's the term gerade, which means even. And what that means is that when you apply the inversion through a given orbital and you have something that remains identical, in other words, the phase remains unchanged, that's going to be an orbital that is gerade. If an orbital is ungerade, well, ungerade means uneven, and you apply the inversion, does not remain identical. Okay, so one type of symmetry is symmetrical, the other one is asymmetrical. All right, so let's look at this by looking at specific orbitals for us to understand this concept of symmetry. Well, it turns out that the s and d orbitals are gerade. All right, let's look at this more closely. So let's focus on the s orbital. In going to the center, the sign of the orbital phase does not change. In other words, you have what is known as a center of symmetry. So let's define this point where we have a plus, which is my representation of the nucleus, a positively charged nucleus. All right, so we'll put a little dot here. Let's say I put an X here on this part of the y-axis, right? And I apply an inversion, so I go through, and I end up right here at an equal but opposite distance from that center. Well, what happened? Did my phase change? And no, the phase did not change. All right, so because of that, the s orbital is gerade. Right, let's do something similar for the d orbital. We're going to define the center. So I'm putting the red dot right here, and I'm going to choose a location. So I'm going to put a location right here, X, and I'm going to invert through that center. So I invert through in equal and opposite direction, and I land right here. All right, and so what do we see? Did the phase change, right? So the coloration is blue. We see these negative signs. It did not change. And because it did not change, that indicates that this is gerade, but we have to make sure that's true throughout. Let's go through another part of this orbital. How about if I start from here? Okay, I go through here and then end up over here. What do we know? do we see any change? And no, we do not. So again, we don't see any change. It turns out that these two orbitals are symmetrical. And it also turns out that they are Gerade. Okay. Now let's look at a representation of the p and the f orbitals. It turns out that the p and the f orbitals are ungerade. All right. So ungerade, in going through the center, the sign of the phase changes. All right. So let's imagine that we're starting. Let's identify our origin being right here, at center. And then we start here as our origin. We invert through. And what happened? When we inverted through there, we see that the phase changes. And that's true of any location that we start from, right? We invert through, and the phase changes. So this is ungerade. What about the f orbital? See, it's a little bit more complex. We have 6 lobes here. We have our center. If we go through, so let's imagine that we start here as a point of context. This is our origin. If we invert through, what happens? We end up with a change in phase. So these are, in terms of the phase, they are asymmetrical. They are ungerade. Okay. Before we move on, I want to ask if you have questions. Isis?
Isis.
Yes.
¿Usted usa esos términos intercambiablemente como sinónimo?
Which?
¿O no? El ungerade and asymmetrical.
In terms of the phase, not the appearance of the actual orbital.
Okay, in terms of the phase.
Because if you look at the p orbital, if you just look at the shape of it, it looks symmetrical. But we're not looking in terms of the shape, in terms of the phase.
I have a question in regards with what you mean with a phase, because I know like
so as I was mentioning before, you're thinking about this as a wave function, right? So you'll have parts of it that will be positive charge, so the positive, and other parts with negative values. So just imagine that you have a region that is entirely positive and a region that's entirely negative. Okay, they're not the same sign, and so you have a difference in phase. And that's true of all of these. Okay.
Yeah,
as you can see, I made sure to give it a representation of charge just to give us an idea, not just coloration, because you often see in books just a color, but we don't really know what that means.
Okay? Yeah, I thought like it was like the phase meant like the shape, not the change in the charge.
It does not mean the shape. It means the actual the distribution for the given wave. Other questions? Okay. All right, let's move ahead. All right, so let's look at this all together then. When we're focusing on orbital energies, well, the energy is determined by the principal quantum number for hydrogen. So the principal quantum number N is very important when we're looking at that. But then for all other elements, the summation of N and L helps to define the orbital energies or the relative orbital energies. There are some exceptions there, and we'll talk about them as we continue on the course. As we also know, energy is quantized, all right? So even though we focus on this wave mechanics, we still appreciate that the energy of the different orbitals, right, in terms of the primary quantum number, will be actually quantized. So we have n equals to 1, n equals to 2, n equals to 3, and so forth. Something that I have alluded to but I have not specified, so here I'm going to be much more specific, is that as you increase the values of n, what we start to see is that the energy levels become closer. Okay, so you see this is a representation of the nucleus, and then here we have the quantum numbers, okay, the n values. But as you are moving away from the nucleus and you have a corresponding increase in energy, well, it turns out that at the higher end, these differences become smaller and smaller. The reason for this is because there's obviously going to be less attraction to the positively charged nucleus, and so there'll be a corresponding less difference between these energies as they're further away from the nucleus. You're going to reach a point. Okay, let's imagine you reach this point up here, where as the electron, okay, let's say we're down here, goes out of this threshold. When it goes out of this threshold, what happens is the electron is released from the atom, right? And it becomes ionized, right? So the electron's released, you have an ion now. And so what we term this as the ionization energy of the atom. The loss of one electron is the first ionization energy. Let me just clear the markings. So the release of an electron is a measure of the ionization energy of the atom. And so that's actually really important, because I have talked about this as the electron moving away from the nucleus, and as you go at a higher energy orbital, the higher the probability of the value of R will be. But what I wasn't so specific about is that you reach a point where you simply are so far away that you lose the electron because of the loss of that electrostatic attraction. All right, so overall rules of thumb for everything that we've discussed today. For the hydrogen atom, only the value of N matters for the determination of energy. So, as we are well aware of, the lower the value of N, the lower the energy of the orbital, the more stable it is. And the reason for that greater stability is because there's a stronger attraction between that electron and the positively charged nucleus. But then, for all other atoms, so here, specifically when we're focusing on polyelectronic atoms, then the summation of N plus L matters. So just to give us a perspective, in a given quantum number N, the energy of the s orbital is less than the energy of the p orbital, which is less than the energy of the d orbital, which is less than the energy of f orbital. Right? This is something that we're familiar with, but we're going to look at it more closely as we continue on. The value of L helps to determine the type of orbital, so orbital type. Okay, there are 2L plus 1 number of orbitals of each type. Okay, so what does that mean? I mentioned this before, but wasn't too specific here. So you have that for the s orbital, remember s equals to a value of 0, right? So you have a total of only one s orbital. The p orbital, so p is an L equals to 1, and you plug it into this equation here, we have a total of 3 p orbitals. D, the total of 5 d orbitals, and F is a total of 7 d orbitals. Within an atom, each of these blocks of orbitals will be degenerate. So remember, these 3 will be degenerate. These 5 will be degenerate. And these 7 will be degenerate. Again, all equal in energy in the atom. Then there are n types of orbitals in the nth energy level. Okay, what does that mean? Well, if we have n equals to 1, there can only be one type of orbital. And what is that one type of orbital? Well, that is the s orbital. N equals to 2. Okay, well, according to this, there can only be 2 types of orbitals. Can anyone guess what are those 2 types of orbitals? And n equals to 2?
S and P.
S and P. Okay, so here is important that we look at the periodic table. So next time we'll look at the periodic table to look at this more closely. The same thing is true, n equals to 3. There will be 3 types of orbitals. So the 3 types will be the S and the P and the D, and so forth. Okay, next is defining the nodes. So there's n minus L minus 1 nodes in the radial part of the wave function. And then with respect to the angular part, there are L nodal surfaces and the angular part. Okay, so then when we add up all these together, the radio nodes and the angular nodes, okay, so that'd be n minus 1 minus n minus L minus 1 plus L, okay, but we're going to have the total of n minus 1 total nodes in the wave function. And that's going to be, again, a combination of the radio and the angular nodes. All right, so we're going to stop here. In our next lecture, we're going to continue on, review some of these concepts just to make sure that we fully understand, especially the symmetry component, as that's a really crucial part of the course. All right, everyone. Well, I want you to have a great weekend, and I will see you in class in person next week. Take care.
Professor,
Yes.
about the book,
Uh-huh.
where can I find the PDF?
Yes, I emailed you. Excuse me. I'm emailing you the PDF, but it is available online. Okay.
Okay, thank you.
All right.
Well, have a great day.
Okay,
Thank
take care.
you.
Have a nice day,
Gracias, buen
Professor.
día.
All right, take care. Great weekend, everyone.